we have our DEP. Now we just have to integrate to get the field. So let's integrate. Let's say that EP, the thing we want, the E field at point P, is the integral of DEP. We're just adding up all the DEPs. And that's the integral of this. But there is something special here. When we have a sigma, that means we're doing 2 dimensions. We have a 2-dimensional charge distribution, which means we have 2 differentials here. Of course, we have to integrate over 2 dimensions for a 2-dimensional thing, which means it's a double integral. We have to actually have 2 sum symbols. One is for dr, and one is for d theta. Okay, we'll work on their limits in a minute. For now, let's just go ahead and write it. We have Ke. I'm going to start pulling some constants out. Sigma is here, and then this is r dr d theta, and this is r squared plus z squared. And we never dealt with the cosine phi. Let's think cosine phi from that drawing. Cosine's adjacent over hypotenuse. Adjacent was z, so there would be a z in here, and we fit it in here. And then the hypotenuse is the square root of r squared plus z squared, so there's another one of these in the denominator, which brings that to the 3/2, if you will allow me to skip a step there. So that's our integral. These two apply to these two, so let's think about the limits for this disk. If we're going to represent the entire disk, we have to integrate the radius from 0 to r, so that can be the radius integral. And if we're going to get the whole disk, we have to go all the way around the circle. So theta has to go from 0 to 2 pi. Okay? So there's our integral. Let's look at it. When you do these 2 integrals, you just do them separately. You just do them one at a time. So in one step, we can do the d theta integral. If all you have is integrating d theta from 0 to 2 pi, the integral of d theta is just theta. And when you evaluate that from 0 to 2 pi, well, theta at 2 pi is 2 pi minus theta at 0 is 0. So this integral just becomes 2 pi. Okay? So let me just write it as 2 pi as part of the constant. So the 2 pi is the theta integral, and then you still have a Ke, and you have a sigma, and actually z is a constant in this case. Z was just how far out are we, so there's really, that's not changing as we move around the disk. So there's our constants, 2 pi, Ke, sigma, and z. And we're left with this integral from 0 to r of what? R, and I'm going to write it like this, r times r squared plus z squared to the minus 3/2. Go ahead and just not write it as a quotient, dr. Similar to how I did that integral when we had the point charge near the rod. We'll just write it this way. Okay, so if we keep going then, EP is, let's keep our constants, 2 pi Ke sigma z. And if we want to integrate this, this one's actually doable. Minus 3/2 becomes minus 1/2. You divide by that, that becomes minus 2. And then you also divide by the derivative. You divide by 2r. The r goes away, so you're also multiplying it by 1/2. Doing that again. And then it becomes this to the minus 1/2. Right? R squared plus z squared to the minus 1/2. I like doing these integrals better writing it out this way than having the square root things in the bottom. It just depends on how you want to do it. And that's evaluated from 0 to r. This is 2 to the minus 1/2. Evaluated from 0 to r. Okay? So we can simplify a little bit. Those 2's go away. It leaves a negative sign sitting there, which is along for the ride. So E, and of course it's on the K direction. So EP equals, let's keep our constants as many as we can out, 2 pi Ke sigma z. And those 2's went away. We pull the negative out like that. And now we plug in big R into the little r. So that becomes 1. I'll go back to quotients now. 1 over big R squared plus z squared minus, and now we plug in the 0 for the r, minus 1 over the square root of 0 plus z squared. Oh, that's just z. Once the r goes away, it's just the square root of z squared, so that's just z. In the k-hat direction, because of symmetry. And, you know, we can make this look a little simpler. I guess if we pull the negative in, it'll switch sides, and these two will switch sides, and we could carry in the z to make that be a 1 and put a z up there if we wanted to make it pretty. I think it's beautiful as it is, but if we could clean it up a little bit, sigma, it might look like this. Pull in the z, 1, switch the order by getting rid of that, 1 minus z over the square root of r squared plus z squared. That's probably about as simple as you'd want to bother to make it. Okay. So there you go. That's a case of doing a disk. There are different kinds of problems you could do. That's sort of the most straightforward disk problem that we can come up with.